In 1925, physics encountered a fact it could not repair. For more than 2 centuries, the universe had been treated as fully describable, every motion traceable, every future state calculable, at least in principle. From Newton's mechanics to Einstein's spacetime, reality was assumed to be there, complete and accessible, waiting to be written down. Then a young physicist, named Werner Heisenberg, removed something essential. Not a particle, not a force, but the idea that physics was obligated to describe what reality is between observations. What followed was not confusion, but precision. A framework that predicted experiments with unmatched accuracy, while refusing to say what exists when nothing is measured. Tonight, we explore how that quiet decision reshaped modern science, technology, and the limits of knowledge itself. We begin with Part 1. If the universe was supposed to be fully knowable, why did physics collapse in 1925? In 1925, physics did not fail because it lacked equations. It failed because its most trusted promise stopped working. For more than 200 years, the physical world had been treated as something that could be fully described, fully tracked, and fully predicted, provided the measurements were precise enough and the mathematics was done carefully. This confidence did not come from optimism. It came from success. Newton's laws had explained the motion of planets with accuracy unmatched in human history. Using the same equations, astronomers predicted the return of comets, the existence of unseen planets, and the exact timing of eclipses centuries in advance. When Pierre-Simon Laplace wrote in the early 19th century that a sufficiently informed intellect could compute the entire future of the universe, he was not exaggerating by the standards of his time. That belief survived even Einstein's revolution. Relativity changed how space and time behaved, but it did not abandon determinism. Einstein's equations still described a universe governed by exact relations. If you knew the distribution of mass and energy, the geometry of spacetime followed inevitably. Prediction remained intact. By the early 20th century, physics appeared nearly complete. In 1900, Lord Kelvin famously remarked that only 2 small clouds remained on the horizon of classical physics. Those clouds, however, were not small. The first appeared in the spectrum of heated objects. Classical theory predicted that a hot body should emit infinite energy at short wavelengths. Experiments showed the opposite. In 1900, Max Planck introduced a mathematical fix, treating energy as exchanged in discrete amounts. He regarded it as a formal trick, not a statement about reality. The second cloud appeared when light struck metal surfaces. Experiments showed that electrons were ejected only above certain frequencies, regardless of brightness. Einstein explained this in 1905 by treating light as localized packets of energy. The explanation worked perfectly, yet it conflicted with the continuous waves described by classical electromagnetism. These anomalies were unsettling, but they were treated as technical problems. Most physicists believed the underlying picture remained sound. The universe was still assumed to possess definite properties at all times. Measurement merely revealed them. Atoms, however, refused to cooperate. Spectroscopy showed that atoms emitted light at sharply defined frequencies. Niels Bohr proposed a model in 1913 in which electrons occupied specific orbits and jumped between them. The model reproduced spectral lines with remarkable accuracy. But no experiment ever observed an electron following those paths. This discrepancy grew harder to ignore. The more precisely physicists measured atomic behavior, the less sense the classical picture made. Attempts to refine electron trajectories failed. Corrections accumulated, but clarity did not. By the early 1920s, the field was crowded with partial rules that worked but could not be reconciled with a coherent picture of motion. Quantization appeared everywhere, yet no one could say what exactly was being quantized. Was it energy, motion, or something deeper? Werner Heisenberg entered this landscape as a young physicist trained in mathematics and deeply uncomfortable with speculation. He was not searching for a new picture of atoms. He was searching for consistency. In 1925, while working under intense pressure and recurring illness, Heisenberg made a decision that quietly changed the direction of physics. He asked a simple operational question: what quantities in atomic physics can actually be connected to measurements? Electron positions inside atoms were not among them. Neither were precise trajectories. What experiments reliably provided were frequencies of emitted light and their intensities. Heisenberg chose to build a theory using only those quantities. This choice was not philosophical. It was methodological. Heisenberg refused to assign physical meaning to variables that could not, even in principle, be checked against observation. The mathematics that emerged was unfamiliar. Instead of numbers that commute under multiplication, the new formalism used arrays of values whose order mattered. Changing the sequence of operations changed the result. This was not a technical inconvenience. It was a physical statement. Soon after, Max Born recognized that Heisenberg's tables were matrices. Together with Pascual Jordan, they developed what became known as matrix mechanics. It reproduced atomic spectra with unprecedented precision. No classical model could match it. But something had been lost. The theory made no attempt to describe what electrons were doing between emissions. There were no paths, no hidden motions waiting to be uncovered. Physics had stopped promising a complete description of microscopic reality. This shift was not widely recognized at first. Many treated matrix mechanics as an abstract tool, assuming a deeper picture would eventually emerge. Yet the structure of the equations resisted reinterpretation. When Erwin Schrödinger introduced wave mechanics shortly afterward, it seemed to restore continuity. But the apparent relief was temporary. Schrödinger's waves did not describe physical ripples in space. Max Born showed they described probabilities. By the time the equivalence of the two approaches was established, the situation was unavoidable. The most accurate theory ever developed did not describe what exists independently of observation. It described correlations between preparations and outcomes. Richard Feynman would later summarize this unease with characteristic clarity. I think I can safely say that nobody understands quantum mechanics. This was not an admission of ignorance about calculations. Predictions matched experiments to extraordinary precision. Atomic clocks, lasers, semiconductors, and later technologies confirmed the framework again and again. Organizations such as NASA and ESA rely on quantum principles daily, from satellite navigation to deep space communication. The difficulty lay elsewhere. The theory worked while refusing to say what was happening between measurements. It offered reliability without imagery. What collapsed in 1925 was not physics itself, but a centuries-old expectation. The expectation that every physical theory must provide a complete narrative of reality. Heisenberg's work demonstrated that precision could survive without that promise. The universe, it seemed, could be handled operationally even when it resisted visualization. Determinism, once the backbone of physical explanation, no longer applied in the way Newton and Einstein had assumed. Yet this was not a retreat. It was a narrowing of responsibility. Physics chose to remain exact where exactness was possible, and silent where it was not. The consequences of that decision still shape every modern experiment, from particle accelerators to space-based observatories. And as attention shifts from this moment of collapse, the next layer of tension appears, because if electrons never behaved the way classical physics claimed, the problem was not only theory, but the unseen motions it insisted on describing. Part 2. Why was the electron never seen doing what physics claimed it was doing? For more than a decade, physics described electrons as if they were moving in precise paths, yet no experiment ever saw even a trace of those motions. This was not a minor oversight. It was a growing contradiction at the heart of atomic theory, one that survived only because the predictions worked while the pictures quietly failed. At the beginning of the 20th century, atoms were no longer speculation. Chemical reactions, electrical conduction, and radioactivity all pointed to a structured interior. What physicists needed was a model that could explain why atoms emitted light at specific colors and never in between. Spectroscopy provided the evidence. When gases were heated or electrically excited, they produced narrow lines at exact wavelengths. Hydrogen, the simplest atom, showed a small set of sharp lines whose spacing followed precise numerical patterns. These patterns were measured repeatedly in laboratories across Europe and the United States. In 1913, Niels Bohr proposed an explanation that appeared decisive. He suggested that electrons could occupy only certain allowed states and emit light when moving between them. The idea reproduced the hydrogen spectrum with remarkable accuracy. It immediately gained acceptance. Yet Bohr's model came with an uncomfortable feature. It described electrons as orbiting the nucleus in defined paths, similar to planets around the Sun, but with one crucial rule added by hand. Those orbits were declared stable without explanation, even though classical electrodynamics predicted that any accelerating charge should radiate energy continuously and spiral inward. Physicists noticed the tension, but the success of the predictions overshadowed it. The model worked where classical physics had failed. Many assumed the missing details would be filled in later. As experiments became more precise, the cracks widened. Bohr's orbits explained hydrogen well, but struggled with heavier atoms. Additional rules were introduced, then more corrections, then entire tables of exceptions. Each fix improved agreement with data, but clarity did not improve. Most troubling was the fact that the orbits themselves never appeared in any measurement. No detector, no scattering experiment, no optical technique ever revealed an electron tracing a path inside an atom. The orbits existed only in calculations. This absence was not due to limited technology. By the early 1920s, experimental physics had become extremely refined. X-ray diffraction was resolving atomic spacing in crystals. Electron beams were being produced and measured with controlled energies. Yet inside atoms, motion remained invisible. The problem was not that electrons were too small to see. It was that the very act of trying to describe their motion assumed classical concepts that no longer applied. This realization emerged gradually. In scattering experiments, electrons behaved sometimes like localized impacts, sometimes like extended waves. The outcomes depended on how the experiment was arranged. The same object refused to commit to a single description. NASA and ESA would later rely on these same principles in particle detectors and space instrumentation, where quantum behavior determines how sensors register signals at the smallest scales. The unpredictability was not noise. It was structure. Bohr himself became increasingly cautious. He emphasized that atomic models were not literal pictures, but tools for organizing results. The orbits, he admitted, were conveniences. This shift marked a change in tone. Physics had long aimed to describe what objects were doing at all times. Now, it was forced to confront the possibility that such descriptions had no experimental anchor. The growing discomfort reached a turning point when Werner Heisenberg chose to abandon orbits entirely. He did not replace them with hidden paths or finer structures. He removed them from the theory. What remained were quantities tied directly to observation, frequencies of emitted light, intensities of spectral lines, transitions between measurable states. The success was immediate and unsettling. The calculations matched experimental data with higher accuracy than any orbital model had achieved. Yet there was no account of what electrons were doing between emissions. This absence was not filled later. It became permanent. As quantum mechanics developed, electrons were no longer treated as tiny bodies following trajectories. They were described by mathematical objects that encoded the likelihood of different outcomes. These objects evolved smoothly in time, but did not represent motion through space in the classical sense. The consequences were profound. Atomic spectra were no longer explained by electrons circling nuclei, but by changes in allowed states. Stability arose not from balanced forces, but from the structure of those states themselves. In laboratories today, including those supported by NASA for space-based atomic clocks, this framework is not optional. It is required. The clocks that guide spacecraft navigation rely on electron transitions whose accuracy depends on quantum descriptions that contain no orbits at all. What survived from the Bohr model was not its imagery, but its discipline. It respected the data. When the imagery failed, the discipline remained. J. Robert Oppenheimer later summarized this shift with quiet precision. The atom is not a thing, but a pattern of possibilities. This was not a retreat from realism. It was an alignment with what experiments allowed. The atom continued to produce exact, repeatable results. What changed was the willingness to claim more than the evidence supported. By the mid-20th century, no serious physicist expected to see an electron orbit. The language persisted in textbooks for teaching convenience, but the research community had moved on. Electron microscopes, which NASA and ESA now use to analyze materials for spacecraft, do not image orbits. They detect interactions. The images are reconstructions based on probabilities, not snapshots of paths. What becomes clear is not that physics somehow failed to observe something. It is that physics learned, over time, to stop holding on to observations that no longer described anything real. As atomic theory matured, the gap between intuition and evidence widened. What felt reasonable to imagine turned out to be irrelevant to what could be measured. This tension did not weaken physics. It sharpened it. By discarding pictures that could never be confirmed, the theory gained precision, stability, and scope. And as this restraint took hold, another consequence became unavoidable. If electrons did not possess definite properties between measurements, then the very idea of what could be removed from theory became the next point of pressure. Part 3. What did Heisenberg dare to remove that everyone else took for granted? In 1925, progress in physics did not come from adding a new entity to the universe, but from removing a question that everyone before had assumed must be answered. This was the unsettling step Werner Heisenberg took when he chose to discard quantities that could never be tied to observation, even though those quantities had been treated as essential for centuries. Up to that moment, physics had been built on a shared expectation. Every theory was supposed to say what objects were doing at all times. Motion meant position changing continuously through space. Cause meant a definite state producing a definite outcome. Even when experiments were difficult, the underlying picture was assumed to exist. This expectation survived repeated failures. Atomic spectra had shown that electrons did not radiate energy the way classical motion required. Attempts to repair the picture by adjusting trajectories only made theories more complicated and less grounded. Still, most physicists held on to the belief that a hidden description must be waiting underneath. Heisenberg did not share that confidence. He was trained during a period when experimental results were accumulating faster than interpretation. Precision spectroscopy had reached a level where frequencies of emitted light could be measured with extraordinary accuracy, while the imagined motions responsible for them remained completely inaccessible. Instead of asking what electrons were doing inside atoms, Heisenberg asked something more restrictive. What does an experiment actually return? The answer was never a trajectory. It was a number, a frequency, an intensity, a transition. This was not a philosophical move. It was a technical discipline. Heisenberg deliberately excluded from his calculations any quantity that could not be connected to measurement, even indirectly. Position as a function of time inside the atom failed this test. What replaced it was unfamiliar. Instead of following an electron through space, the theory tracked how measurable quantities changed from one experimental situation to another. The focus shifted from motion to relation. The mathematics that emerged surprised even its creator. When operations were carried out in different orders, the results did not agree. In classical physics, the sequence of calculations never mattered. Here, it did. This property was not a flaw. It matched the structure of atomic data. Transitions between states depended on the order in which experimental conditions were applied. Nature itself was enforcing the rule. Max Born recognized that these rules corresponded to matrix mathematics, a branch of algebra rarely used in physics at the time. Together with Pascal Jordan, he formalized the approach. The resulting framework predicted atomic spectra with unprecedented accuracy. Nothing in the equations referred to hidden paths. There were no placeholders waiting to be filled by future discoveries. What could not be measured was not approximated. It was removed. This decision marked a quiet boundary. Physics no longer claimed responsibility for describing what happens when no observation is possible. It claimed responsibility only for the relationships between experimental arrangements and outcomes. Many physicists found this uncomfortable. The idea that a theory could be complete while refusing to describe underlying motion ran against centuries of habit. Einstein himself resisted this constraint, believing that a deeper, observer-independent account must exist. Yet the data did not support that hope. Every attempt to restore hidden variables that behaved classically introduced contradictions with experiments. Measurements of interference, scattering, and atomic transitions consistently favored Heisenberg's restraint. Over time, this approach became foundational. Quantum mechanics did not grow by adding interpretation. It grew by refining what could be stated without ambiguity. NASA and ESA rely on this discipline in practice, even when it remains counterintuitive. Instruments aboard spacecraft detect signals at energy scales where classical descriptions fail. Engineers do not model electrons as moving along tiny tracks inside sensors. They use transition probabilities and response functions derived directly from quantum theory. This operational focus makes technologies possible. Atomic clocks used in satellite navigation depend on transitions whose timing is predicted without any reference to electron motion. The accuracy, reaching deviations of less than 1 second over billions of years, comes from abandoning classical pictures entirely. The same logic governs detectors used in astrophysics. When observatories measure faint signals from distant galaxies or cosmic background radiation, the interaction between radiation and matter is treated probabilistically. The calculations succeed precisely because they avoid claims about unobservable intermediate states. This restraint was later summarized by John Archibald Wheeler in a sentence that reflects the core of Heisenberg's move. No phenomenon is a phenomenon until it is an observed phenomenon. The statement does not deny reality. It defines the boundary of physical description. Phenomena, in the scientific sense, are what experiments register. Heisenberg's decision also changed how physicists evaluated questions. Instead of asking whether a quantity exists, they asked whether its existence could be tested. If not, it carried no weight in theory. This rule was applied unevenly at first. Schrödinger's wave mechanics appeared to reintroduce continuity and spatial structure. But careful analysis showed that the wave function did not describe a physical wave in space. It encoded probabilities for outcomes. Once again, unobservable structure was excluded. The wave function itself could not be directly measured. Only its consequences could. This pattern repeated across quantum theory. Spin was introduced not as literal rotation, but as a property revealed through measurement. Entanglement described correlations, not signals traveling between particles. Each time, physics advanced by narrowing what it claimed. The discipline did not reduce predictive power. It increased it. The cost was conceptual comfort. Many familiar questions were no longer answerable. What path did the electron take? At what point did it choose a result? These questions had no experimental meaning. Rather than force answers, the theory declined to ask them. This refusal was not surrender. It was control. Over decades, this stance proved durable. Every precision test of quantum mechanics, from particle accelerators to space-based experiments, has confirmed its predictions. No experiment has revealed the hidden motion that earlier theories assumed must exist. What emerges here is not a sense of loss. It is a stricter kind of discipline. Heisenberg chose to set aside elements that could not be anchored to evidence, even when they felt indispensable to the old picture. Physics continued forward by accepting that constraint. Once this way of thinking took hold, an unexpected consequence became visible. If entire categories of description could be removed without weakening prediction, then the limits of what physics could say were not temporary gaps waiting to be filled. They were built into the structure itself. And when order itself gains physical meaning, the sequence of actions can no longer be treated as interchangeable. That realization did not arrive in a lecture hall or a laboratory at full strength, but during a period of illness and isolation, far from the centers of physics. Part 4. How did illness and isolation on Helgoland reshape the laws of nature? In the summer of 1925, the foundations of physical law shifted not in a grand laboratory, but on a small, windswept island, shaped by calculations written by a physicist whose body was failing and whose sleep had nearly vanished. This was not a moment of inspiration born from comfort or clarity. It was pressure, isolation, and an unforgiving confrontation with mathematics that refused to compromise. Helgoland is a narrow strip of red sandstone in the North Sea, about 60 kilometers off the German coast. In the early 20th century, it was known less for science than for its harsh air and isolation. Werner Heisenberg was sent there by his mentors not to think more clearly, but to recover. He suffered from severe hay fever, asthma, and recurring allergic reactions that left him exhausted and unable to work for long stretches. On Helgoland, away from pollen and academic debate, his physical condition improved only slightly. Sleep remained elusive. Long nights stretched on, broken by short periods of calculation and constant self-correction. Heisenberg was not searching for elegance. He was trying to make a set of stubborn experimental facts agree with each other without contradiction. By that point, the crisis in atomic theory was severe. Spectral data were precise. Transition frequencies in hydrogen had been measured repeatedly and independently. Any viable theory had to reproduce those numbers exactly. Approximate agreement was no longer acceptable. Heisenberg worked with tables of values drawn directly from spectroscopy. Each number corresponded to an observable transition between atomic states. Instead of imagining electrons moving through space, he treated these transitions as the primary elements of the theory. This approach demanded relentless consistency. Every step had to preserve measurable relationships. If a calculation produced a number that did not match known spectra, it was discarded. There was no room for interpretation or adjustment. The mathematics either aligned with data or it failed. During these nights, Heisenberg encountered a disturbing pattern. When he combined quantities associated with transitions, the order in which they were combined mattered. This was not an artifact of approximation. It was unavoidable. In classical physics, order does not matter. Measuring position then momentum gives the same result as measuring momentum then position. On Helgoland, Heisenberg found that this assumption collapsed at the atomic scale. The mathematics refused to restore symmetry. This was not a moment of insight followed by relief. It was shock. Heisenberg initially suspected an error. He repeated the calculations, checked the assumptions, and re-derived the relationships from scratch. The result did not change. The equations held together only if non-commuting quantities were accepted as fundamental. This meant that the structure of atomic behavior could not be mapped onto classical motion. The framework was internally consistent, but it no longer described trajectories or hidden processes. Later, reflecting on this period, Heisenberg described the experience with a phrase often quoted by American physicists: "I was looking at a strangely beautiful interior." The phrase did not refer to visual elegance. It referred to coherence. Despite his exhaustion, the mathematical structure fit together without contradiction. Each part reinforced the others. When Heisenberg returned from Helgoland, he presented his results cautiously. Max Born immediately recognized that the calculations corresponded to matrix algebra. This realization transformed a private struggle into a formal theory. Together with Pascual Jordan, Born helped place the work on solid mathematical ground. What became known as matrix mechanics was not intuitive, but it was exact. It reproduced atomic spectra with precision unmatched by any previous approach. Importantly, the theory did not allow interpretation to override results. Where classical ideas failed, they were not repaired. They were excluded. This discipline distinguished the Helgoland work from earlier models. Bohr's atom had succeeded by imposing restrictions that lacked derivation. Heisenberg's framework imposed restrictions because the mathematics demanded them. The environment mattered. Helgoland offered isolation from academic pressure, but not from intellectual responsibility. Without lectures, seminars, or debate, every assumption had to justify itself on paper. Physical weakness played a role as well. Heisenberg did not have the energy to pursue multiple speculative paths. He followed only what remained consistent after repeated checks. This constraint narrowed the theory until only what was unavoidable survived. In hindsight, the island functioned as a filter. Anything that relied on imagery rather than measurement was stripped away. What remained was a framework tied directly to experiment. This approach continues to shape modern physics. When NASA and ESA design instruments to detect faint signals from space, they rely on quantum descriptions derived from the same discipline. Detectors respond to transitions, not trajectories. The James Webb Space Telescope, for example, measures spectral signatures produced by atomic and molecular transitions billions of light-years away. The interpretation of those signals depends on quantum mechanics that traces its lineage directly to Helgoland. None of this requires electrons to be imagined as moving along paths. The predictions depend only on the structure of allowed states and transitions. The theory works because it does not claim more than experiments support. The Helgoland episode is often retold as a story of sudden insight. That framing misses the central feature. The mathematics did not yield easily. It resisted interpretation and forced acceptance through consistency alone. What reshaped the laws of nature was not inspiration, but refusal. Refusal to bend equations to fit intuition. Refusal to preserve familiar concepts when they conflicted with data. The island did not create quantum mechanics. It concentrated it. Under physical strain and isolation, the discipline of observables, only physics, became unavoidable. When the work was published later that year, it marked a clear boundary. Physics would advance by tightening its claims, not expanding them. The cost was loss of visual narrative. The gain was reliability. Helgoland stands as a reminder that scientific revolutions do not always begin with new ideas. Sometimes they begin when old assumptions are no longer defended. When the mathematics itself no longer commuted, the sequence of physical actions could no longer be treated as interchangeable. Order stopped being a matter of convenience and began to carry physical weight in a way no earlier theory had permitted. Part 5. Why does quantum mathematics refuse to respect order the way nature once did? There was a moment when physicists realized that simply changing the order of actions could change the outcome of an experiment, even when nothing else was altered. This was not a mathematical trick. It was a physical fact, one that quietly overturned the assumption that nature always allows its properties to be arranged neatly, one after another, without consequence. For centuries, order had been irrelevant in physics. In classical mechanics, measuring one property and then another never changed the final description. Position could be determined before momentum or after it, and the result would be the same. This assumption was so deeply embedded that it was rarely stated. It was simply how nature was expected to behave. This expectation survived, even as physics entered the atomic scale. Early models assumed that, although atoms were small, their internal properties could still be revealed piece by piece. Measure carefully enough, and every detail would fall into place. Matrix mechanics broke that assumption without announcing it. When Heisenberg, Born, and Jordan formalized the theory, they noticed that the mathematical objects representing measurable quantities did not behave like ordinary numbers. Performing one operation and then another did not produce the same result as reversing the order. At first, this looked like a technical inconvenience. In most branches of physics, such issues can be resolved by changing notation or choosing a better coordinate system. Here, no such adjustment worked. The difference persisted no matter how the equations were arranged. This persistence pointed to something physical. The theory was not saying that calculations were awkward. It was saying that the properties being calculated could not be treated as simultaneously well-defined. To understand why, it helps to return to the experiments that motivated the mathematics. In atomic spectroscopy, the outcome depends on how the atom is prepared and how it is probed. Changing the sequence of interactions changes the observed frequencies and intensities. This is not experimental error. It is reproducible structure. Consider how quantum states are accessed in practice. An atom is first placed in a specific condition, often by absorbing energy. It is then allowed to emit radiation, which is measured. Reversing these steps is not possible. The sequence defines the result. Matrix mechanics encoded this asymmetry directly. The mathematical operations representing these steps retained their order. Swapping them produced a different outcome because the physical situation was different. This realization reframed the meaning of non-commutativity. It was no longer an abstract property of symbols. It was a statement about how nature responds to intervention. The implications extended quickly. If two properties do not commute, then they cannot both be assigned definite values at the same time. This is not due to measurement disturbance. It is because the theory itself does not contain a state in which both properties are simultaneously fixed. This insight reshaped the interpretation of uncertainty. Limits on precision arose not from flawed instruments, but from the structure of the physical description. The mathematics was reflecting a boundary built into how properties exist. Experiments confirmed this repeatedly. In measurements involving spin, for example, the result depends on the order in which orientations are tested. Measuring along one direction changes the possible outcomes of a subsequent measurement along another. Reversing the order produces a different statistical pattern. These effects are now routine in laboratories. They are used deliberately in quantum control experiments and in technologies developed for space-based instrumentation. Agencies such as NASA and ESA rely on precise quantum behavior in detectors where non-commuting properties determine sensitivity and noise. The mathematics does not explain this behavior by appealing to hidden mechanisms. It does not claim that properties exist but are inaccessible. It states that the properties are defined only within specific experimental contexts. This contextual nature is what makes order matter. Each operation reshapes the state. The next operation acts on something that has already been changed. Classical physics avoids this because it assumes a fixed underlying reality. Quantum mechanics does not make that assumption. It tracks how preparation and measurement combine to produce outcomes. The resistance to accepting this was strong. Many physicists hoped that non-commutativity would disappear in a deeper theory. Decades of experiments have shown the opposite. The effect is fundamental. Freeman Dyson summarized this discomfort with characteristic restraint. Nature uses mathematics we are not yet comfortable with. The discomfort comes from expectation, not from failure. The mathematics works with extraordinary accuracy. It predicts spectral lines, transition rates, and interference effects to levels confirmed repeatedly. In modern applications, this structure is unavoidable. Quantum sensors used in space missions depend on sequences of operations whose order determines the signal. Reordering those steps degrades performance in predictable ways. The James Webb Space Telescope, for example, relies on detectors whose response depends on quantum transitions governed by non-commuting operators. The interpretation of faint infrared signals from distant galaxies depends on this framework. None of these technologies require an image of particles carrying all properties at once. They require a consistent rule for how outcomes change when operations are reordered. What Part 5 reveals is not a breakdown of logic, but a refinement of it. Nature does not guarantee that all properties can be arranged in a single sequence without consequence. The mathematics reflects that constraint directly. Order matters because the theory does not permit a complete list of simultaneous attributes. Each measurement selects a context. The next measurement inherits the consequences. This understanding did not arise from speculation. It emerged because every attempt to ignore order failed experimentally. The mathematics survived because it matched reality more closely than any alternative. As quantum mechanics matured, non-commutativity became a guide rather than a nuisance. It identified which questions could be asked meaningfully and which could not. Once outcomes themselves became sensitive to order, uncertainty could no longer be treated as a technical flaw. No refinement of instruments could remove it, because it was no longer coming from measurement at all. It arose from the internal structure of quantum states, written into how those states evolve. Part 6. Is uncertainty a failure of measurement, or a feature of reality itself? What if the universe would remain incomplete, even under perfect observation, even with instruments that introduce no disturbance at all? This was the disturbing implication that emerged when physicists finally understood what the uncertainty principle was actually saying, and why it could not be repaired by better technology, sharper tools, or more careful technique. In its early reception, uncertainty was often misunderstood as a practical problem. The story sounded simple. Measuring an electron's position requires interacting with it, and that interaction disrupts its motion. According to this view, uncertainty was a consequence of clumsy interference. Improve the instruments, and the limitation would shrink. This explanation was comforting. It preserved the idea that the universe itself remained fully defined, and only human access was flawed. But this explanation did not survive close examination. The mathematical structure of quantum mechanics pointed to something far more restrictive. The limits did not arise when measurements were performed. They were present even before any measurement occurred. To understand this, physicists examined how quantum states are defined. A quantum state does not assign a single value to every property. Instead, it specifies a range of possible outcomes, each with a calculable likelihood. Some properties can be sharply defined together. Others cannot. This was not a statement about ignorance. It was a statement about structure. The theory did not contain states in which certain pairs of properties were simultaneously precise. The uncertainty principle emerged directly from this fact. It was not added as a rule. It was derived from how quantum states are built. The same mathematical relationships that produced non-commutativity also produced uncertainty. This became clear through repeated experimental tests. In systems prepared with well-defined position, momentum distributions broadened exactly as predicted. When momentum was constrained, position spread accordingly. These effects were observed regardless of measurement technique. Precision experiments confirmed this across many platforms. Cold atom laboratories demonstrated uncertainty limits using atoms cooled to fractions of a microkelvin. Even under these controlled conditions, the limits remained unchanged. The conclusion was unavoidable. Uncertainty did not come from disturbance. It came from the fact that quantum states do not encode complete sets of simultaneous properties. This understanding reshaped how physicists thought about knowledge. The limitation was not epistemic. It was ontological. The theory itself restricted what could exist in a single state. Leonard Susskind summarized this distinction with precision. Quantum mechanics is not about what we know, but about what can exist. This statement reflects a central lesson. The uncertainty principle is not a statement about human limitation. It is a statement about how physical properties are distributed across possible outcomes. Consider how this plays out experimentally. In interferometry experiments, particles prepared in narrow spatial regions show wide spreads in momentum. This spread is not random noise. It is required by the structure of the state. Space-based missions confirm this routinely. Atomic clocks flown by NASA and ESA rely on transitions that obey uncertainty relations with extraordinary precision. The clocks function because these limits are stable, not because they can be overcome. The James Webb Space Telescope detects faint infrared signals whose interpretation depends on quantum transitions constrained by uncertainty. The reliability of these observations depends on accepting, not avoiding, those limits. The same applies in particle physics. In high-energy collisions, particles are produced with distributions that reflect uncertainty relations built into the theory. These distributions match predictions across many orders of magnitude. Attempts to explain uncertainty as measurement error consistently failed. Even hypothetical measurements that introduce no disturbance still obey the same limits. The theory does not allow sharper states to exist. This realization marked a shift in how questions were framed. Instead of asking how precisely a property could be measured, physicists asked whether a state allowing that precision existed at all. In many cases, the answer was no. The restriction was not technological. It was structural. This did not weaken predictive power. On the contrary, it strengthened it. By respecting these limits, quantum mechanics delivered predictions that matched experiments with unmatched accuracy. The misconception persists in popular explanations, but within physics, the issue is settled. Uncertainty is not a flaw. It is a defining feature of quantum description. This feature also explains why classical intuition fails at small scales. Classical objects are assumed to possess complete sets of properties at all times. Quantum systems are not described that way. Instead, properties emerge through interaction. The state encodes possibilities. Measurement selects outcomes consistent with that structure. This framework governs technologies used daily. Magnetic resonance imaging, semiconductor devices, and quantum sensors all operate within uncertainty limits that cannot be bypassed. In space exploration, these principles are indispensable. Instruments designed to detect weak signals from distant objects rely on quantum-limited sensitivity. Engineers do not attempt to remove uncertainty. They design systems that function within it. The uncertainty principle thus becomes a guide rather than an obstacle. It defines what kinds of precision are meaningful. It prevents theories from making claims that cannot be realized physically. This discipline traces directly back to Heisenberg's original insight. By discarding unobservable quantities, the theory avoided false precision. Uncertainty replaced determinism, not because the universe became chaotic, but because the description became honest. The consequence is subtle. Physics did not lose control over prediction. It lost the promise of complete specification. As experiments continued to confirm this structure, the debate shifted. The question was no longer whether uncertainty could be eliminated. It was whether physics should even attempt to describe what lies beyond these limits. Uncertainty did more than limit what could be known. It quietly forced physics to change what it meant by description itself. Reality was no longer captured by listing objects and their properties, but by accounting for which outcomes occur, and how those outcomes are related. Part 7. When physics stopped describing reality, what did it choose to describe instead? When physicists finally accepted that particles do not carry definite properties between measurements, the crisis was not that reality disappeared, but that the language of physics had to change its target. The shock was quiet and technical, yet profound. If electrons no longer followed paths, if atoms no longer possessed fixed attributes at every instant, then what exactly was physics describing with such extraordinary accuracy? For centuries, the task of physics had seemed clear. Objects existed in space and time. They had properties such as position, speed, and energy. The job of theory was to describe how those properties evolved. Measurement revealed what was already there. Quantum mechanics dismantled this assumption without replacing it with an alternative picture. Instead, it introduced a different focus. Physics would no longer describe objects as they are presumed to be when unobserved. It would describe the structure of outcomes that experiments reliably produce. This shift did not happen overnight. Early formulations still spoke in the language of particles and waves, even when that language no longer matched the mathematics. Over time, it became clear that what survived experimental testing was not imagery, but prediction. At the heart of the new framework was a mathematical object that did not resemble anything familiar. It did not represent a trajectory or a shape in space. It encoded the likelihood of different measurement results. From this object, probabilities could be calculated with remarkable precision. These probability amplitudes did not describe what a particle was doing. They described how often specific outcomes would occur under defined experimental conditions. Change the conditions, and the amplitudes changed accordingly. This was not a retreat from realism. It was a narrowing of responsibility. Physics restricted itself to statements that could be checked against observation. Niels Bohr articulated this stance with careful restraint. Physics concerns what we can say about nature. The sentence is often misunderstood as evasive. Within the discipline, it served as a boundary. Physics would no longer claim to describe hidden processes that left no trace in measurement. This boundary proved powerful. Once the theory focused on outcomes, rather than imagined behavior, contradictions disappeared. Interference patterns, atomic spectra, and scattering experiments all fit within a single framework. Consider the double-slit experiment. When particles are sent one at a time toward a barrier with two openings, they produce an interference pattern over many trials. No description of individual paths accounts for this. The pattern emerges from accumulated outcomes. Quantum mechanics does not attempt to say which slit a particle passes through when no measurement is made. It calculates the probability distribution of detection events on a screen. Those calculations match experiments exactly. The same logic governs atomic transitions. An atom prepared in a given state does not gradually change its energy. It produces discrete emission events. The theory predicts the frequencies and relative intensities of those events, not the internal process between them. This outcome-based approach scales upward. In particle accelerators, physicists do not track particles through invisible trajectories. They predict distributions of collision products. Detectors record those products, and the statistics are compared to theory. NASA and ESA rely on the same framework in space science. Instruments aboard satellites and telescopes detect photons, electrons, and ions as discrete events. The interpretation of those detections depends on probability amplitudes calculated from quantum theory. The James Webb Space Telescope, for example, observes infrared photons emitted by distant galaxies. Each detection is an outcome. The theory does not describe the photon's journey as a continuous path. It predicts detection rates and spectral distributions that align with observation. This emphasis on outcomes also clarified the role of measurement. Measurement is not a passive act that reveals pre-existing values. It is an interaction that selects one outcome from a structured set of possibilities. The structure is encoded in the quantum state. The state evolves smoothly according to precise rules. When an interaction occurs, the state yields a specific result with a calculable likelihood. This view avoids unnecessary speculation. It does not claim that particles lack reality. It claims that reality, at this scale, is not captured by assigning fixed properties independent of context. What physics chose to describe instead was the relationship between preparation, interaction, and outcome. These relationships are stable, repeatable, and precise. They form the basis of all quantum predictions. The reliability of this approach is beyond dispute. Quantum electrodynamics predicts experimental results to accuracies better than 1 part in a billion. No classical description approaches this level of agreement. Importantly, this success does not depend on interpretation. Different philosophical views exist, but the operational core remains unchanged. Physics continues to describe outcomes, not hidden processes. This restraint has practical consequences. Engineers designing quantum sensors or communication systems focus on controlling outcome probabilities. They do not attempt to manipulate unseen trajectories. In space missions, this approach is essential. Detectors measuring weak signals from distant objects operate at quantum limits. Their performance depends on understanding outcome statistics, not on reconstructing microscopic histories. The shift from objects to outcomes did not reduce the scope of physics. It expanded it. By abandoning unnecessary descriptions, the theory became applicable to regimes where classical intuition fails completely. This change also clarified long-standing debates. Questions about what happens between measurements lost their urgency because the theory did not require answers to function. What mattered was that every prediction about outcomes could be tested. The discipline proved resilient. Over decades, experiments became more refined, not less. Each test reinforced the outcome-based structure. The transition described in Part 7 is therefore not a story of abandonment. It is a story of focus. Physics concentrated on what could be stated precisely and verified repeatedly. By doing so, it preserved its predictive power while discarding claims that could never be confirmed. The cost was loss of familiar imagery. The benefit was unmatched reliability. As this framework settled into practice, it revealed a deeper tension. If physics describes outcomes rather than underlying reality, then disagreement over interpretation becomes unavoidable, especially when the theory works perfectly but refuses to explain itself in traditional terms. Quantum mechanics proved extraordinarily successful where predictions were concerned. Yet that success never settled what the theory was actually saying about reality itself. Agreement arrived in calculation, not in interpretation. Part 8. Why did Einstein reject a theory that worked almost perfectly? How unsettling must a theory be to trouble the same mind that reshaped space and time? A theory so accurate that every test confirmed it, yet so incomplete that its most famous critic could never accept it. This tension did not come from failure. It came from success without explanation, from predictions that worked while refusing to say what, beneath them, was truly real. Albert Einstein did not oppose quantum mechanics because it was wrong. By the early 1920s, he knew very well that its calculations matched experiments with extraordinary precision. He had contributed directly to its foundations, explaining the photoelectric effect in 1905 by treating light as localized packets of energy. Without that step, much of quantum theory would not exist. His discomfort arose later, as the theory matured. Quantum mechanics began to abandon the idea that physical systems possess definite properties independent of observation. Instead of describing what is, it described what can be measured. For Einstein, this was not a technical detail. It struck at the purpose of physical theory. Einstein's own work had reinforced a different expectation. In relativity, measurements depend on the observer's motion, but the underlying structure remains objective. Space and time change their measurements, yet space-time itself exists as a real entity governed by precise equations. Observers disagree about coordinates, not about reality. Quantum mechanics did not offer this reassurance. Its core equations predicted probabilities, not outcomes. They worked flawlessly, yet they refused to assign values to properties before measurement. The theory functioned, but it did not describe an observer-independent world in the way Einstein expected. This difference became clearer during debates in the late 1920s. At conferences and in correspondence, Einstein pressed the same point repeatedly. A physical theory, he argued, should describe reality as it exists, not merely catalogue experimental results. His concern was often summarized in a single sentence that has echoed for decades: God does not play dice with the universe. The phrase is frequently misunderstood. Einstein was not objecting to probability as a tool. Statistical methods were central to thermodynamics, a field he respected deeply. His objection was to probability as a fundamental description of reality. Quantum mechanics appeared to say that events occur without definite causes, that outcomes are selected from distributions without deeper explanation. For Einstein, this signaled incompleteness, not novelty. He believed that beneath the probabilistic formalism, there must exist additional variables, restoring determinism and objectivity. These variables, though unknown, would ensure that physical properties existed whether or not they were observed. This belief led directly to the most famous challenge to quantum mechanics. In 1935, Einstein, together with Boris Podolsky and Nathan Rosen, published a paper now known as the EPR argument. The argument did not claim quantum mechanics made wrong predictions. Instead, it demonstrated that if the theory were complete, it would imply what Einstein considered unacceptable features. In particular, it allowed correlated systems to exhibit linked outcomes across large distances without specifying underlying causes. The setup was simple in principle. Two particles interact and then separate. Quantum mechanics assigns them a shared description. Measuring one particle allows precise prediction of the outcome for the other, even when they are far apart. According to the theory, this correlation does not require any signal traveling between them. The shared state already contains the necessary structure. For Einstein, this raised a problem. If the distant particle's property becomes definite only when the first is measured, then either information travels faster than light, or the property did not exist beforehand. Einstein rejected both options. He concluded that the theory must be incomplete. This challenge sharpened the debate. Niels Bohr responded not by adding hidden structure, but by reaffirming the framework's limits. The theory, Bohr argued, does not describe properties independent of experimental context. Demanding such a description was insisting on a classical notion that no longer applied. For decades, the dispute remained unresolved. It was philosophical in appearance, but experimental in consequence. If hidden variables existed, they should eventually produce testable differences. In the 1960s, this possibility was clarified mathematically by John Bell. Bell derived conditions that any local, deterministic theory would have to satisfy. Quantum mechanics predicted violations of those conditions. Experiments followed. Over the next decades, increasingly precise tests measured correlations between entangled particles. The results consistently matched quantum predictions and violated Bell's inequalities. These experiments were not isolated. They were repeated with photons, electrons, and atoms, across increasing distances and with improved controls. Modern versions, including space-based tests supported by ESA, have closed major loopholes. The conclusion was clear. No theory preserving both locality and observer-independent properties could reproduce the data. Quantum mechanics survived every test. This did not mean Einstein was careless. His objection identified a real tension. The theory predicts outcomes without describing an underlying mechanism that exists independent of measurement. That tension remains. In modern physics, this debate shapes interpretation rather than calculation. Different frameworks attempt to explain what the mathematics represents, but none alter its predictions. Experiments continue to confirm the same probabilistic structure. NASA and ESA rely on this structure in practice. Quantum correlations are used in precision timing, navigation, and emerging communication technologies. Engineers do not resolve the philosophical debate. They use the predictions. The James Webb Space Telescope detects photons whose behavior is governed by quantum statistics shaped by the same principles Einstein questioned. The telescope does not require an interpretation of reality to function. It requires accurate probabilities. Einstein's resistance, then, was not denial. It was insistence. He insisted that physics should describe a world that exists independently of observation. Quantum mechanics offered a world that reveals itself only through outcomes. This difference reflects a deeper divide between explanation and prediction. Prediction succeeded spectacularly. Explanation, in the classical sense, did not follow. The power of quantum mechanics lies precisely in this separation. It delivers reliable results without requiring a narrative beneath them. For many physicists, this is sufficient. For Einstein, it was not. He accepted the success but rejected the conclusion that nothing deeper could be said. His criticism sharpened the theory and forced clarity about its claims. In that sense, Einstein did not stand outside quantum mechanics. He shaped its foundations by challenging them. The debate he initiated continues to define how physicists think about reality, measurement, and description. The predictions never failed. What remained unsettled was what those predictions were meant to describe. A theory that performs flawlessly but stays silent about its own meaning does not lose credibility. It shifts the focus of scrutiny from accuracy to interpretation. Part 9. If quantum mechanics builds our technology, why can't it explain itself? How can a theory that powers nearly every modern technology still refuse to tell us what, at the deepest level, is actually real? This is not a rhetorical puzzle. It is a practical and persistent tension at the core of quantum mechanics, a theory whose predictions have been confirmed more precisely than any other framework in the history of science, yet whose meaning remains unsettled nearly a century after its birth. Quantum mechanics works. That fact is beyond dispute. The transistors inside computers, the lasers in communication systems, the atomic clocks guiding satellites, and the detectors aboard space observatories all rely on quantum principles. NASA and ESA missions depend daily on calculations rooted in quantum theory, from spacecraft navigation to the interpretation of faint signals arriving from billions of light years away. And yet, despite this success, physicists continue to disagree on what the theory is saying about reality itself. This disagreement does not affect calculations. It does not change experimental predictions. It persists precisely because the theory functions perfectly without resolving it. This situation is unusual in physics. In most cases, predictive success and conceptual clarity advance together. Newton's laws described both how objects move and why their motion makes sense within a coherent picture of forces. Einstein's relativity reshaped space and time, but it also offered a clear geometric account of gravity. Quantum mechanics broke this pattern. From its earliest days, the mathematical formalism produced correct results while resisting a single, shared explanation of what those results meant. The source of the problem lies in what the theory chooses to describe. Quantum mechanics does not describe objects carrying definite properties through time. It describes how experimental preparations lead to statistically distributed outcomes. This shift, introduced quietly and deliberately, left open the question of what exists between those outcomes. Different answers to that question give rise to different interpretations. Each interpretation attempts to explain what the mathematics represents, without altering the mathematics itself. This is why the interpretations disagree philosophically but agree experimentally. One approach treats the quantum state as a complete description of reality, even though it encodes only probabilities. Another views the state as a bookkeeping tool, summarizing information about measurements without claiming physical existence. Others introduce additional structure, such as hidden variables or multiple branches, to restore a sense of underlying completeness. What unites these views is that none of them change what experiments observe. Interference patterns, atomic spectra, and entanglement correlations appear exactly as predicted, regardless of interpretation. This creates a strange divide. Engineers can design devices with extraordinary reliability using quantum equations, while physicists debate what those equations describe. The theory delivers answers while declining to justify them in familiar terms. Sean Carroll summarized this situation with characteristic clarity. Quantum mechanics works astonishingly well, but it's deeply mysterious. The mystery is not about accuracy. It is about meaning. The equations specify how probabilities evolve and how outcomes are distributed. They do not specify what, if anything, exists independently of measurement. This gap became evident early. After the formalism of quantum mechanics was completed in the 1920s, physicists immediately began asking how to understand it. These questions did not slow the theory's adoption. Laboratories continued to confirm its predictions. Over time, the gap widened. Quantum electrodynamics achieved agreement with experiment to parts per billion. Solid-state physics explained the behavior of materials with remarkable precision. None of this required resolving what the wave function represented. In space science, the same pattern holds. The James Webb Space Telescope relies on quantum models of atomic and molecular transitions to interpret infrared spectra. These models predict line strengths and absorption features with accuracy verified repeatedly. The telescope does not require a decision about whether probability amplitudes are physical objects or calculational tools. This separation between use and meaning is unsettling to some physicists. A physical theory, they argue, should describe what exists, not just what is observed. Quantum mechanics appears content to stop at observation. Others see this as a strength rather than a weakness. By limiting itself to operational statements, the theory avoids speculative commitments that cannot be tested. It remains tightly coupled to experiment. The interpretational landscape reflects this divide. Some interpretations emphasize realism, insisting that the theory must describe an observer-independent world. Others emphasize pragmatism, treating the theory as a tool for organizing experience. Crucially, no experiment has yet distinguished between these views. Every precision test confirms the same statistical predictions. Bell-type experiments rule out certain classes of hidden explanations, but they do not select a single interpretation. This leaves quantum mechanics in a unique position. It is both complete in practice and incomplete in explanation. It tells us how outcomes occur, without telling us what underlies them. The situation has practical consequences for how physics progresses. Research continues by refining predictions and extending applications, not by resolving interpretation. Funding agencies and laboratories prioritize accuracy and capability. NASA and ESA missions exemplify this approach. Space-based quantum sensors, atomic clocks, and radiation detectors operate at fundamental quantum limits. Their design depends on precise probability calculations, not on metaphysical commitments. This does not mean the question of meaning is ignored. it remains active in foundational research. Conferences, papers, and debates continue to explore how the theory might be understood more deeply. What makes the problem persistent is that quantum mechanics offers no internal criterion for choosing among interpretations. The mathematics is silent on what it represents. It specifies how amplitudes evolve and combine, but not what they are. This silence is deliberate. It traces back to the original decision to focus on observables and outcomes. By doing so, the theory avoided false claims. It also relinquished narrative completeness. The result is a framework that advances without closure. Each new experiment strengthens confidence in the predictions while leaving interpretation open. This openness has shaped modern physics. New theories, such as quantum field theory and efforts toward quantum gravity, inherit the same structure. They extend the mathematics while leaving the question of meaning unresolved. Some physicists argue that a deeper theory will eventually restore clarity. Others suspect that the demand for a single ontological picture may itself be misplaced. Both positions coexist within the field. What cannot be denied is the effectiveness of the current framework. Quantum mechanics underpins nearly every precise measurement made today. Its limits define the boundaries of sensitivity, resolution, and control. The paradox of Part 9 is therefore not failure, but success without closure. A theory can build technologies, guide exploration, and reshape science while leaving its own meaning unsettled. This is not a temporary embarrassment. It has endured for generations. Each attempt to force a single explanation has either contradicted experiment or reduced to philosophical preference. Quantum mechanics remains exact where it speaks and silent where it does not. That silence is not accidental. It reflects a boundary set at the theory's origin. Near regimes where spacetime itself begins to lose definition, this boundary stops being abstract. A theory that never depended on a fixed ontology may be the only kind that remains workable once classical structure fades. When time and space themselves approach their limits, interpretation is no longer a philosophical luxury. What quantum mechanics revealed earlier returns here as a physical necessity. Part 10. At the Planck scale, did Heisenberg's lesson become unavoidable? What if the final boundary of physics is not a wall we have yet to reach, but a line we have already crossed, where even time itself stops behaving like something that can be described? At the smallest scales known to physics, the universe does not merely resist measurement. It resists definition. This realization did not appear suddenly. It emerged gradually as physicists pushed their theories toward regimes where quantum mechanics and gravity must both apply at once. For decades, these two frameworks have worked with extraordinary success in their own domains. Quantum mechanics governs atoms, particles, and fields. General relativity governs spacetime, gravity, and the large-scale structure of the cosmos. Individually, each theory is precise. Together, they are incompatible. The conflict becomes unavoidable at scales, defined not by human choice, but by fundamental constants. When the speed of light, the gravitational constant, and Planck's constant are combined, they produce natural limits. One of these limits is Planck time, approximately 5.39 times 10 to the power of -44 seconds. This number is not arbitrary. It marks the scale at which quantum fluctuations of space-time itself can no longer be ignored. Below this interval, the very notion of a smooth sequence of moments loses operational meaning. To understand why, physicists examined what it would take to measure such short durations. Any clock capable of resolving intervals smaller than Planck time would require energies so concentrated that gravity would dominate. Instead of revealing shorter times, the measurement would collapse into a black hole. This is not a technological limitation. It is a structural one. The laws of physics themselves prevent time from being resolved beyond this scale. Here, Heisenberg's lesson returns with force. In quantum mechanics, properties that cannot be measured are removed from the theory. At the Planck scale, even space-time intervals fall into this category. There is no experiment that can assign a precise duration smaller than Planck time. As a result, modern physics has no justification for describing what happens within such intervals. This does not imply ignorance, waiting to be solved. It implies a boundary. Theoretical efforts to unify gravity and quantum mechanics confront this boundary directly. Approaches such as loop quantum gravity and other quantum spacetime models do not treat spacetime as a continuous backdrop. They replace it with discrete structures whose smallest elements are defined near the Planck scale. In these models, time does not flow smoothly. It emerges as an approximate concept when many discrete processes are considered together. Below that scale, the theory does not attempt to describe temporal order in the classical sense. This restraint echoes Heisenberg's original decision. Instead of forcing classical concepts to apply where they fail, modern physics limits its claims to what can be defined operationally. Evidence supporting this approach comes indirectly from cosmology. Observations of the cosmic microwave background, mapped with high precision by space missions supported by NASA and ESA, show fluctuations that trace back to quantum processes in the early universe. These fluctuations are consistent with quantum descriptions applied to spacetime itself. Yet even here, the theory does not describe a moment-by-moment evolution at the Planck scale. It describes statistical features that survive into observable epochs. The James Webb Space Telescope extends this picture further. By observing galaxies formed within the first few 100 million years after the Big Bang, it probes conditions where quantum and gravitational effects intersect. The data confirm large-scale predictions, but offer no access to Planck-scale detail. This absence is not accidental. It reflects the same principle seen throughout quantum theory. Physics advances by describing what can be tested, not by speculating beyond that reach. At the Planck scale, even spacetime becomes an inferred concept rather than a directly measurable one. The smooth geometry described by general relativity breaks down. Quantum uncertainty applies not just to particles, but to distances and durations themselves. Attempts to describe shorter times introduce contradictions. The theory becomes inconsistent unless it relinquishes classical meaning. This is not failure. It is self-consistency enforcing restraint. John Archibald Wheeler captured this shift with a sentence that resonates strongly here. We are no longer observers of the universe. We are participants. The statement reflects a technical reality. At extreme scales, observation cannot be separated from the structure being observed. Measurement defines the limits of description. This insight does not diminish physics. It clarifies it. Theories remain predictive precisely because they do not claim access to regimes that cannot be operationally defined. Heisenberg's observables-only approach thus becomes unavoidable. It is not merely a choice suited to atomic physics. It becomes a necessity when space-time itself enters the quantum domain. Modern physics now operates with an explicit awareness of its boundaries. It describes phenomena within those boundaries with unmatched precision. Beyond them, it remains silent. This silence is disciplined. It prevents false certainty. It allows theories to remain consistent across scales. As a result, progress no longer means eliminating all limits. It means identifying which limits are fundamental. The Planck scale represents one such limit. It marks where time, as a measurable sequence, ceases to exist. Below it, physics does not extend classical description. This realization reshapes how knowledge itself is framed. Not everything that can be imagined can be described. Not everything that can be described can be measured. The success of physics comes from respecting this hierarchy. Predictions remain accurate because they stay within definable domains. In this sense, the journey that began with Heisenberg reaches its natural conclusion. The refusal to describe unobservable motion at the atomic scale becomes the refusal to describe undefined time at the Planck scale. The pattern is consistent. Where measurement ends, description ends. This does not close the story. It stabilizes it. Future theories may extend the boundary, but they will do so by redefining what can be observed, not by ignoring limits. For now, physics stands on firm ground precisely because it knows where that ground stops. As this final part settles, the universe remains vast, structured, and deeply ordered within the limits we can access. Beyond those limits lies not mystery to be conquered, but boundaries to be respected. And as you rest, letting these ideas slow and soften, it is worth remembering that the same principles guiding the smallest scales also guide our understanding of the largest ones. The cosmos does not demand complete description to remain coherent. It requires only careful attention to what can truly be known. I hope this video brings you a sense of reassurance as you close out the day that even when physics reaches its limits, the universe continues to operate in a consistent, stable, and ordered way. Good night.